let's get started. I'll share my notebook. When you folks can see it.
Yeah, we can see it now.
Fine. Okay, so the next several lectures, what we're going to do is start with or continue our journey along the path of understanding convolutional neural networks a lot better. Move next to coding an autoencoder, identify some problems why an autoencoder doesn't train quickly or give us good results when we try to train it, and using that as the launching pad or more of the reason for providing or getting a framework established so that we can flexibly train a variety of neural networks. And compared to the past several lectures, I think starting with this lecture, but more importantly, moving through the next couple of lectures, the subject matter gets a little bit more involved and detailed. So if you have any questions, please feel free to stop and ask, because it's through discussion we understand better rather than it being a monologue. That said, I believe where we left off last week is the fact that we had imported the image digits network, saw that we could potentially create filters, and the filters are these kinds of tri-tree tensors, and they could be describing, for example, a top edge, or in using the top edge, we could then apply it to the 28 by 28 image and then slide the filter across the image so that it's able to detect edges, as it were. We then coded a simple apply kernel function, which kind of was able to apply the kernel, and then we kind of tried to also write the code simply to step it over the entire image. And then we came up with a left edge and did the same, and the result was this. We also saw what is the result of applying a 3x3 excuse me, a 3x3 kernel to a 4x4 image results in this 4x4 pixel image as the result. Okay. With that background, let's continue our move through the convolutional networks and how we can then accelerate the multiplication process of the filters with the underlying image. So here, and you can follow the link. This was the original paper, if you will, that was written to show what one particular graduate student way back did in order to accelerate the computation of the kernels multiplying the underlying image. So there's a NumPy implementation as well, but let me use a single image from the paper to illustrate and stop sharing my screen of the notebook. I'll start sharing the PDF, if you will, so I can kind of explain and let me know when you can see the image of the PDF.
Yeah, we can see that now.
Okay, so what we're trying to do here, again, keep in mind, is that we're trying to accelerate the matrix multiplication that results when we want to multiply a kernel with the underlying image and then slide it across the image. So conceptually, again, I'll just illustrate one example. You can read the paper, link for which is provided in the notebook itself. But here is the way that the unfolding, which helps us accelerate the matrix multiplication works. Let's say we have this 3 by 3 image, and we have 2 by 2 filters. And so what we have on the top are 2 kernels, each of which is, because the image, unlike in this case, is 3 channels. So this is the first channel, this is the second channel, and this is the third channel. So similarly, obviously, the kernels will have the same number of channels, 3 filters, 3 channels for each filter. So this is filter 1 and this is filter 2. Now, how do we compute the output in an accelerated manner? What we can do, and what is actually happening, is we take this filter and put it on top of the image right here, right? So that means the image here first is the values are 1, 2, 1, and 1. And then we step this filter to the right. So we'll then have 2, 0, 1, 3. So what you will see here, the input features of these inputs that we are providing, you can see that 1, 2, 1, 1 has been flattened. Then the next step, as I said, is step right. So that's 2, 0, 1, 3. So that's the next flattened row here. As you can imagine, in convolution, the next step after we've gone step right is to step down below. So the next value will be 1, 1, 0, 2, which is what you see here. And then you move to the right again. So it should be 1, 3, 2, 2, which is what you see here. That's what you do with respect to the input filters. So following my explanation, that's how you unroll this guy. So it will be 0, 2, 0, 3, followed by 2, 1, 3, 2. And you can kind of go step by step and figure out that this is what is happening here. Similarly, these filters are flattened. And how are they flattened? Well, 1, 1, 2, 2 is what you multiply this initial by. So you flatten it, make it 1, 1, 2, 2. The next channel of the convolutional kernel is 1, 1, 1, 1, which is why you have a 1, 1, 1, 1 here. And then there is a 0, 1, 1, 0. So that's what you have here. The next filter, the second convolutional kernel, I'm using the kernel and filter language interchangeably. So you get 1, 0, 0, 1, 2, 1, 2, 1, 1, 2, 2, 0, right? So then what this enables us to do is all of the matrix multiplications that need to happen as you move these filters or kernels across the input can all happen in a single matrix multiplication. This entire input matrix multiplied by this kernel matrix gives you the output, and the output can then be folded back again because the output that's provided is 14, 20, 15, 24. And you just fold that back into the shape you want, which is 14, 20, 15, 24. Right? So I think the point is that you can accelerate the kernel movement across the input matrix by flattening the kernels and reshaping the input, or unfolding the input features and doing a matrix multiplication and then folding it back again. Now that we've kind of seen this visually, let's go back to our notebook and see the implementation in code. You should be able to see it now. So you can see here, we'll be doing exactly the same thing. PyTorch conveniently gives us the unfold function. The unfold function does the basic unfolding of the input matrix that I had just shown you on the PDF of the paper. And that's what the unfolding of the input with respect to a 3 by 3 kernel. Of course, the size of the kernel that you apply is important. So the input is unfolded. As I have notes here, the reason we do a none, none, and then comma, comma, or the two colons, is we only have the 28 by 28 input matrix, but what PyTorch expects is the batch size as the first dimension, the number of channels as the second dimension. In our case, both of these don't exist. So we provide them because that's expected, and then we convert the input to a float, and then we unfold it, and we get the output of a 9 by 276. You can do the math. 26 by 26 about gives you 676. That's why you get this result. Then you flatten the kernel into a single flattened 1 by 9 matrix, which is equivalent to the right side of the kernel matrix that we saw flattened in the PDF. We do that here. And then we do a matrix multiplication of the unfolded input times the flattened value. So it's 1 by 9 times 9 by 676, which will give us a 676 value. Right? And then we reshape the result into a 26 by 26 image. Right? So that's kind of what happens as a result of the left edge view that we have, the left edge view tensor that we have stepped through this 28 by 28 image, converting it into a 26 by 26 value. Now, what he shows in the next 3 cells is simply that we have our own code as he has continued to practice that it's important to code it ourselves just using Python, and then switch to the case of using other frameworks and so on, so we understand what's happening in the code. So first we do that by applying the left kernel and then doing the ij and motion or movement across the image. It takes us this much time. On the other hand, when we do it with the matrix multiplication that we've just done by using the IM to call, or basically the unrolling of the input and the flattening of the kernel. And this is again an intermediate step. He says there is a convolutional 2D function that's coded in PyTorch that you can use. And let's still say we apply the left edge to the input image and time that, and you can see that that takes us even a quarter of the time that our flattened personal Python code of unfolding using PyTorch convolutional 2D network is even faster than that. So the next several steps illustrates that we had a left edge, a right edge. We could have a diagonal edge as well, and we could do the same thing of showing the diagonal edge, what it looks like. You could have, this is a diagonal edge going from the left to the right. You could have a opposite diagonal going this way, going from the right top to the bottom. And that's the image here. So now what we begin to do is, let's take a batch of images and apply not just a single kernel, which was a 3 by 3 kernel of just the left edge or the right edge. Now we are going to say 4 kernels, left, right, top, and or 2 diagonals, and the left and the right edges. So we describe, or the first step, grab 16 images. And the important thing to note, and this again, I keep calling it out because it often confuses me, is this is not the last channel or the last index. This is the second index. That's why I write a note to myself to say, when I look at this, remember that it would have been better if it had been stated as colon, none, colon, colon, because there's still 28 by 28 images to follow. It's just, and it's just that those end colons aren't necessary in PyTorch, so they're left out. But that often tends to confuse me, so I prefer to write it myself, including the last 2 And then we have the edges. We've created the 4 edges. And that's a 4, 1, 3, 3. And now if we do batch features is, let's say, convolutional 2D of the batch of images and apply the edge kernels to the batch of images, then, and again, while the answer is available here, I would encourage you to kind of think through what the result would have to be or should be according to the calculations yourself before you see the result. And obviously, since there are 16 images with 4 channels, in this case, the input channel is just 1, 28 by 28, and you've seen that there's a reduction of 2 by 2 pixels when we go through the stride 1, 16, 1, and so applying it results in, since there are 4 channels in the output, there's 16 images, and the images become 26 by 26 in shape. Right. So that's what is listed here. The output shape shows we have 16 images in the min batch, 4 kernels, 26 by 26 edge map. We started with 28 by 28, that lost 1 pixel from each side. So what we are checking here is that we get the same results. The fact that we have done it with 16 images should not change anything. It's just that the batch size is 16. We are doing the same multiplication over 16 images. That's the only difference. The output continues to be 4 by 26 by 26. Since we've done individually each of the channels and showed that we got 1 by 26 by 26, so when we put them all together, we get 4 by 26 by 26. So we can see the image, what it looks like, and we can look at what the 4 channels, so that for each of the channels, what do they look like? And obviously, each of those would refer to the left, right, and the 2 diagonals. Okay. The next several topics or brief mentions he makes is that the importance of padding and how that enables us to keep the size of the output activation map. That is, when we multiply the kernels with the input that we provide, we want the shape to not change and be identical. Or we might want the shape to, for example, become half the size of the input image. Depending on what we want, or stated alternatively, we can vary the padding and the stride in order to get images to remain the same size as our input image or change its size accordingly. So here is the example of a 5 by 5 input, a 4 by 4 kernel, and 2 pixels of padding. And when we do this, which is a 5 by 5 input with 2 pixels of padding, and then apply a 4 by 4 kernel to it, we end up with a 6 by 6 activation map. So let's look at that image. So see here, we have a basic image which is a 5 by 5. And always when we talk about padding, it's padded on all sides by the same amount. So a 2 by 2, a padding of 2 implies that it's padded on top and bottom by 2 pixels, on the left and the right by 2 pixels. And then we begin to step a 4 by 4 kernel. So the 4 by 4 kernel, including the padding, is placed at the extreme left edge. That generates the first pixel using the 4 actual pixels of the image and a lot of padding on the left and on the top. And then we step it, assuming we still step to a stride of 1, it will shift right by 1, generating the next pixel in the resultant output map, step once more, and it generates, and so on and so forth. And then once it's done moving from left to right, it will move down by 1 pixel and do the same thing. And the result of those convolutional multiplications will result in a 6 by 6 activation map. Okay, so the important thing here is how do you know what the size of the activation map would be, and so on and so forth. And invariably, the formula that is used in order to determine the size of the output activation map is this equation given here. Right? So in each of the dimensions, this is the height and the width. The height of the output map would be the height of the input map plus 2 times the padding. Dilation is another parameter, but typically we can just assume the default, at least currently, to be 1. And so this just assume for all our calculations right now is just 1. And the kernel size is the size of the kernel in each dimension. And you do the math, and this indicates that we take the floor. And you can do this math, and since in our case we are mostly dealing with square images, the resultant H and W would be identical. But these are given in case we do the same thing with rectangular images with the height and width being different. So this is the formula you use in order to get the resultant output activation map that we seek. And you can again do the same calculation of a 4x4 kernel with a 5x5 input and 2 pixels of padding, right? And calculate what that will give, or that will result the output in the output activation map. So in general, what we also see is if we add a kernel of size ks, and typically only the first figure is mentioned because again we typically use square kernels. So if we say a kernel size of 3, it means a 3x3 kernel. And ks being an odd number, such as a 3 or a 5 or a 7, then the necessary padding on each side to keep the same shape of the output as the input is the ks divided by 2, or integer divided by 2. So this would mean, for example, that if we had a ks of 3 integer divided by 2 is 1. When we just do the divide, you get 1.5, but then it's an integer divide, so the result is just 1. So if we choose a 3x3 kernel and we have padding on each side as 1, then we would continue to get the same shape as the input image. We could move over 2 pixels after each of the kernel application, and this is known as a strike 2 convolution, right? And a strike 2 convolution typically would reduce the size of the image to be half the input size. Again, you can calculate that using the same formula I shared a little bit earlier. So a 3x3 kernel with a 5x5 input, a strike 2 convolution, and 1 pixel of padding. So you could put in these values. Stride is 2, input is 5x5. So H in will be 5, stride is 2, padding is 1, dilation is 1, and the kernel size is 3 into this equation here, and calculate H out. And let's see, if we did that, you'll find that for a 5x5 image with a 3x3 kernel with a strike 2, the output is 3x3, which is what is illustrated in this type. Okay, so become quite adept at kind of having this formula handy or memorized in order to be able to quickly determine what the output sizes of the various convolutional networks and filter usage would result in. Okay, so moving along and applying the things we've learned to a little more complicated convolutional networks, what we do is we take NN is the xtrain.shape. Remember that we had xtrain as the mnist images and ytrain are the labels. Because of the label being from 0 to 9, we make it plus 1. The number of hidden layers is 50. We are doing a linear network. So the linear network goes from m, which is the number of inputs, to the NH, which is 50, and then there's a ReLU activation in between, and another linear network that takes us from the number of hidden layers to the number of digits of classes that we have, right? Now, the interesting thing here is this is the network that we had, but what we want to do now is use the convolutional neural networks in order to get a similar result. But when we try to use the convolutional neural networks to go from, let's say, one channel to, for example, let's just pick a number, 30 channels, and our kernel size is 3, and we keep a padding of 1, and then we put a ReLU, and then again we use a convolutional network to go from 30 to 10, much like a linear network, then the interesting thing is that we obviously continue to get the last 2 dimensions to be the size of the image, or depending on what we choose in terms of steps or stride size and the padding, we can get a halving or we can get the same size. But we continue to get 2 last dimensions of height and width, which is not what we had when we used the linear network. So this is just an illustration to show that if we did exactly what I talked about, and we continue to get this 28 by 28 output, that's kind of not what we want, right? We want this to go away eventually, these last 2 dimensions, in order for us to be able to predict the classes. And the prediction of the classes is these 10 classes that we are interested in predicting. Which class, by that, which label does each of the image have? So what we do is we change the convolutional neural network. We call the inputs coming in, the number of channel inputs coming in as Ni, the number of filter outputs, that is the number of output channels that the convolution creates, to be Nf. This Nf will also be equal to the number of filters that we use as part of the convolution. You can recall that by reminding yourself that when we used 4 filters in the very simple top edge, left edge, and 2 diagonals, we got 4 channel output. So similarly, when we say NF here, the output resulting will also be NF. So this is the number of inputs. This is the number of output channels. The kernel size is given here, and the stride default is given as 2. And then here we provide an activation flag, which is if the flag is 2, we insert an activation between or after we do the convolution. So we can define con layer as 2 steps. The result of the input passed through a kernel of kernel size ks with a padding of ks divided by 2, integer divide, stride, NF, and an optional activation, right? So that's what a definition of con is. Okay. So now we can define a simple CNN, which is again a sequential set of layers, and look at what happens to the image as we take it through a series of such convolutions, followed by activations. Since if the activation is 2, we do insert activation after the convolution, after the con2d of a ReLU. So first, in this particular instance, the input channels coming in are 1. So we go from 1 channel to 4 channel with a stride of 2. A stride of 2 reduces the image to a 14 by 14, right? And then we go through from 4 to 8, we double the channels again. We use stride 2 again, and that reduces it to 7 by 7. Then we use 2 channels again, and stride 2 again, and go from 8 Ni to NF of 16. That reduces it to 4 by 4. Then the last stage, we go from 16 input channels to and keep the number of channels the same, which is 16. And that further, because the stride is 2 in each of these convolutions, continues to reduce it to a 2 by 2. Finally, because we want to get output, as I said, and get rid of this last 2 by 2, we convert, we do a 16 channel, output channels of 10. And again, because it's a stride of 2, we get an output with the last 2 dimensions being a 1 by 1. Now, the code for flatten, if you look in PyTorch, simply removes any single dimensions provided to it. Therefore, what flatten will do is convert the last 2, or eliminate, I should say, the last couple of unnecessary unit axes, so that our output becomes just the batch size times the number of channels, the number of channels being our indicator of the number of classes that we are seeking. So that's what we define the simple CNN to be. And so now when we apply the simple CNN to the input XP, we get a 16 by 10 output. So that's kind of what we need, right? So we apply the X images, the training images, then the validation images, create the data set as we have seen before of the train and the X images and the Y train, the labels. Same thing with the validation images and the labels. And here's a function he defines that he'll continue to use over the next several notebooks. Essentially, if you are on a Mac, I guess the NPS is for you. The device is essentially typically either some form of a GPU, as in graphics processing unit. So what you want to do in a system is move the data from the memory of the CPU onto the memory of the GPU. You have to kind of do it explicitly, move it onto the GPU, and then you can utilize the functionality of the GPU. Depending on what you have in your system, that could be either a Mac, or if you have a GPU in the system, like I'm doing with Colab right now, then that is indicated by a positive return from torch.cuda is available. And therefore, we choose either a Mac GPU by first part, or a CUDA NVIDIA GPU, or if we don't have either, we revert, or we default, I should say, to a CPU. So that's essentially what this code does. And then depending on whether it's a torch tensor, then you just move it onto it. If it's a mapping, you obviously will need to move the values of the mapping to the device. So that's what you do here. And basically you move the class of if you just provide it an X value. So that's what this does. And then we just use the PyTorch collate. You can go ahead and look at what that does, but we just, since we have coded this ourselves before, we're now free to use it from PyTorch. So what we do is you collate it and move the batch, apply the default collate from PyTorch, and shift it to whichever device we have in the system, depending on operating on. Okay. Now, I just wanted to show you the code for getDLS so we don't forget what it is. It basically says return getDLS function, essentially says return a data loader of, so it will return us 2 data loaders because there is a train DS and a valid DS. So you have to supply it the train and validation data set, the batch size, and any other keyword arguments it takes, and boom, we get back the 2 data loaders, just to recollect what getDLS does for us. So you can see we do that. From Torch, we are importing an optimizer. We'll kind of learn a lot more about what optimizers are and what they are used for. Essentially, they help us, as we saw actually in the previous lesson. We provided the parameters, in this case of the simple CNN, and we provide the learning rate, and they're using the STD optimizer. So we provide the batch size, the learning rate, it's fairly high, and then getTLS was something we created or coded ourselves in the last lecture, therefore, or 2 lectures back in the dataset notebook. We get the data loaders, we get the optimizers, and again, what did our fit function look like previously? This is what it looked like previously. So when we fit, we just kind of put the model in the training mode, and for each of the X and Y in our train data loader, calculate the loss, backpropagate, use the optimizer to step zero it, and we set the model in the eval mode. The reason for the train and eval mode will become obvious as we move through the rest of the lectures. Then, since in eval mode, we no longer want to compute the gradients, we do this with .nograd. Then we calculate we just set up the loss accuracy and count, and again go through each batch in the valid data loaders. We conduct the prediction, calculate the number in the batch, add it to count, calculate the total loss, the total accuracy, print out the values, and then return the loss divided by the total count, so the average loss and the average accuracy. That's what our fit function is. It helps to kind of keep in mind where or what our code is at each state, because we'll be changing or modifying each of these as we move forward. So we just got to remember that loss and accuracy is what the fit function returns. That's another reason, because it's hard to keep track of what we're changing. It's good to know what this returns. And personally, I find this somewhat annoying, but the way Demi codes is, the first function that's applied to fit is the number of epochs. So you just passes it in as 5. That's another reason I tend to use this, because I can't recall what the first value would have to be, and so on. And of course, you could also do fit open bracket, and that will give you the parameters to be supplied. But anyway, we run and get the loss and accuracy. Okay. As it's running, let's keep moving forward, because I think I was unable to get the desired we have chosen a learning rate of 0.4. Thing to notice is that as we get closer to what the desired smaller loss, it's advisable, and we'll see why and understand it in much more detail. But here it just kind of illustrates that we get a better figure eventually that we are after, that is a better accuracy, by gradually lowering the learning rate after a certain amount of training has been accomplished. So after 5 epochs, if we change the learning rate that we are using in the optimizer and train for 5 more epochs, you'll see that the accuracy has improved on the validation set to 97.7%. Right. The other thing he illustrates is we have used 2 networks so far. One is the linear network, and the other is the convolutional neural network. How do the parameters of the 2 networks compare? So we can use the simple number of elements method for each item in our model, and then sum them all up in order to calculate the total number of parameters in each of our 2 models. So the first, we do that for the linear model. So it tells us that the simple 2-layer neural network, where we went to 50 and from 50 hidden layers to 10, gives us 39,760. We do the same thing for the convolutional neural network. And you can see the reason, or among the reasons why a convolutional neural network is often used to analyze images or in a lot of image processing, because you get really good results, but at the same time, you do it much more efficiently, because the number of parameters in the convolutional neural network is just 5,274 compared to the number of parameters in the linear layer, which was 39,760. So not only are you getting better results, you're getting better results while doing a lot less computation. Right. So the other thing to understand is the kind of basics of convolutional arithmetic. In an input of size 16, which is a batch size, and one channel, 28 by 28 image, the axes are BS, that's for batch size. Then we have the number of channels, which is typically represented by N, or channels, CH, or C, and then height and width. So this is the format, if you will. So the format of our input is NCHW, right, where the N refers to the batch size. TensorFlow, which is not the framework we are using, uses NHWC, or channels last. That is, it does 16 28 by 28 by 1. So channels show up last. And there are some reasons why the performance of channels last is typically faster. And more recently, PyTorch also supports this, but the default for PyTorch is NCHW. Right? So that's something to keep in mind. And in our case, we have one input channel, 4 output channels, and a 3 by 3 kernel for the first layer of our simple CNN. So simple CNN 0, and then again the index 0 is the first con 2D that we have used. Remember that our con 2D, or remember that our simple CNN itself has what we have coded as con, and the con has 2 sequential layers within it, an activation layer, which follows the con 2D layer, right? So that's the reason why the simple CNN 0 says go into the simple CNN because the first, which would be a con layer, and then go into the con layer and pick the first, which is index 0, and that's the con 2D. And for that con 2D, the input channels are 1, the output channels are 4, the kernel size is 3 by 3, stride is 2 by 2, padding is 1 by 1. So, okay. So what he is illustrating here is, what are the parameters that we're trying to learn? The parameters we're trying to learn are the values of this channel, right? Which is 4 channels of kernel size 3 by 3. So notice that we're trying to learn is the parameters of these filters. And since we have 4 filters each of shape 1 times 3 by 3, so you can do the math to figure out how many parameters are there for that particular con layer. Right. Now, if in our case, we have just, since MNIST images are just single channel, we just have 1 input channel. But if the input image were RGB, then the input image would have 3 channels. And so each of our 4 filters would also have that many channels. And so the result would be 4 filters each of shape 3 by 3 by 3. Right? But that's not the case in our case. By that I mean for MNIST. So the MNIST result will be 4 channels, 4 filters, 1 channel input, 3 by 3. So that's those are the parameters that we're trying to learn. And then since there are 4 channels, the bias value will just be 4. Okay. Again, I would encourage people who aren't very familiar with this to work with multiple examples of convolutional sizes and kind of push through the math, understand how the math works to the output activations as well, or the output shape, as well as the number of parameters anticipated in each of the layers. The next concept he tries to explain is essentially that of a receptive field And let me see. And I believe you folks would not be able to see this. So let me again switch and try to bring it up. Are you able to see what is on my screen? I think values aren't important because if I were to zoom in, I kind of tend to lose the macro point I'm trying to make. So I'll continue to stay with these eye-challenging graph just to illustrate the concept of what is a receptive field. Can you folks see my screen?
Yes, we can see it.
Okay, so the fundamental idea here is, let's say we start with the image, which is that of a 7 in the leftmost image that I've shown here. And then we apply 2 filters and we get the output. And then we apply 2 filters each to each of these 2 outputs. And then we get the output from that, which is the contour here. And then we max spool. We haven't dealt with max spool layer yet, but think of it conceptually as just taking the max value, if you will, and that results in the output that we see here. And then we calculate the dense weights, and in the net result of all that, let's say, is the activation that we see here. The point he's trying to illustrate is a single value eventually in the output in the output activation map, after you have gone through multiple steps of the convolution. For example, we went through 4 or 5 steps, right? We went from an input image of 28 by 28 all the way down to 1 by 1 and then flattened it. So when we do that, let's say we take a single value, and if we were to say what are its immediate precedents, that is, what in the max spool layer or the dense weight influences this value, you can do that in Excel by tracing that. Take it one more time. It tells you what inputs that is impacted by. And as you move through this example, the point he's making is you begin to see that a single value in the output activation map is impacted by a significant chunk of the input activations. The size of the input activation that eventually impacts the value of a single pixel in the output is called the receptive field of that output. And you can kind of play with the Excel sheets that he provides in the notebook to understand the concept of a receptive field, which, as I mentioned, is essentially the size of the input image that influences the value of a single pixel in the output. Okay. Finally, just like I mentioned at the very end, so far we have been dealing with a single channel input. What happens when we use a 3-channel RGB image? So the last few cells just indicate the calculations, if you will, of a convolutional neural network using a 3-channel image. So a color picture is a rank 3 tensor. That means the input channel, the NI in a instead of it being 1 would be 3. So you take the image of a grizzly bear, not have it located here. Okay, so I'm just not going to execute the code here, but just explain it. In this case, the permutation is done in order to move the H and W to the beginning and the channels to the end. That's the reason you see the permutation. And then you see the plotting of the image, and the channels are red, green, and blue. And the idea in this case is the convolution that happens over the RGB image. In what is meant by that is a kernel, which is a 3x3 in the edge and width dimension, now will have also a depth, as it were, or a width, and that would be 3 deep. And that multiplies the input image as we slide over, and the kernels, the 3 deep kernel multiplies the 3-channel image in order to produce the resultant output for each of the pixels. And that's shown in this diagram. So, for example, if we have a 3x3 kernel, the 3x3 red portion of the kernel multiplies the red channel, the green multiplies the green channel, which is the second depth of the same filter, and this is the blue, and that multiplies the blue. And all of these are then added together to yield the resultant output of the output image. And the number of channels that we'll get in the output will be determined by the number of filters that we have chosen, which is the NF value. Okay, that's essentially the convolutional notebook. Any questions for the basics of this notebook? Any comments from anyone? No? Okay, so we keep moving. The next step that we do is to push through, and in effect, in this lecture, while the topic is autoencoder, unfortunately, I thought he was going to explain kind of how autoencoders work, variational autoencoders, and so on and so forth. But that's not what he does. He just basically introduces the concept of an autoencoder, tries to autoencode an MNIST fashion data set, which is very similar to an MNIST digit data set. The size of the image is the same, except that the images are those of various cloth items that we wear, and tries to predict or use an autoencoder, runs into problems with the speed at which it can be done, or with the flexibility at which it can be done, and the quality of the output. And that he uses as the motivation to launch into the next couple of lectures, or this lecture and most of the next lecture, where he builds a framework which is referred to as the learner, which essentially allows us to have incredible flexibility in terms of how we can configure the training of networks. Okay, so let's run. So as I mentioned, we're using an image and label. In this case, it's the fashion MNIST data set that we download from Hugging Face. We do the in-place decorator If you are not familiar, I think you need to go back and look at what we've done in a couple of lectures back. I think in the dataset notebook, it essentially conforms to the Hugging Face requirement of returning the batch, but because of the in-place decorator, while at the same time doing it in place. We define a batch size to be 256. Remember the DSD with transform I, say basically apply this transform, and what you get out of that is a TDS data set. For some reason, Google. Okay. Apologize. Google doesn't seem to want to give me any GPUs currently. Let's see whether I can change. Really is on a B100. It's not. While it's doing its stuff, let's at least move through since I've kind of commented most of the code. A batch size is 256. The transformed data set, which means we apply the transformation to the data set, is what we get as TDS. And then we choose the train portion of the TDS. That
You can use the P4s as well.
You're right. I'm just trying to save my units for other work. But if this fails, I'll switch. Okay. As it runs, let's continue to move forward. We just use the collate dict function that we had seen earlier to convert our transform data set, which is passed TS, and we call that an instance of the that of CF. So that means a collated version of our data set. Now, what we want is the collation to be done. First, we take the data set, transform it, then we collate it, and then remember that before we execute any of the training functions and so on, we want to move it to the GPU, whichever we have. So that's done using, actually, in this case, we use toDevice of the output, which is the CF, which is the collate dict of B. Remember that we are using this data set from Hugging Face, so it's more a collate dict function that we need to use. That's that. And then the collate underscore function moves the collated values to whichever device we have. If you're running on a Mac, it will move it to MPS and so on and so forth, as we just saw in the last notebook. And then we get data loaders, which would be the data loaders of the value, the batch size provided to it. And for K and V in the DSD being the data set that's provided. Okay. So it's just a set of steps we go through to eventually get the loaders, which is what we are after. So we got to go through different steps, transform it, collate it, and provide it with the batch size, because it's a data set that's being transformed and collated, and then as a result, get the data loaders. And then we get DLS, which is the data loaders, to which we pass the transform data set with the batch size, and we say the collate function is this new collate function that we're getting. And then we get the training and the validation portions and grab a batch from DT, which is our train. So we get the labels from ps.featuresy.names, which provides us the names for the images we see, and the labels are these. As I mentioned, it's a bunch of images of various things we wear: a t-shirt, a trouser, a pullover, a dress, a coat, and so on and so forth. Okay, so here, remember that these are things or steps that you had gone through, I believe, in the basic Python or the dataset related notebooks. What we're trying to do here is get the labels to fit with the indices that we'll be getting as part of our Ys. So for the same batch, which is YB:16, that is the Y values for the first 16, and then the star is just unpacking it. And remember that item getter is a decorator in a sense, because it returns a function, and that's called a label getter. And then when we apply the label getter to these labels, what you get are the titles. Okay. And all this just to print the titles on top of the images. So show images and pass in the titles. So you can see there's an ankle boot, there's a t-shirt, there's what a t-shirt top looks like, a dress, pullover. This is, I thought you would have a different label for these two, but all three of these show up as ankle boot. And there is sandals, variety of sandals, shirt top, variety of t-shirt tops, sneakers, pullovers. But we need to kind of classify the images. And again, there are 50, the rest of the macro or hyperparameters are in a sense, or I should say the data parameters are the same: 50,000 input values and 10,000 validation, 50,000 training, 10,000 validation, and so on. So let's say we first classify using the same sequence of images or a sequence of convolutional networks that we've used. So CNN is just copy pasted from the previous notebook. So you kind of go down 14, 7, 4, 2, 1, and then flat. So that's what we do here. And when we try to run it, it does run, but it runs very slowly. And the reason for the reduction in speed or the slow speed at which the convolutional network executes are many, but some of the reasons are that in each of the our input for the fashion image data set, each image is a PNG image. And what that means is in our transform, where we use transform I, we need to convert that into an image. So that we use to provide an input. So that takes a significant amount of time. So if you look at the dataset dictionary before the data is transformed, for MNIST, we had all our data set loaded into memory as a single big tensor. In this case, that's not the case. We have to convert each of the PNG image, and that in turn causes a problem because our data loader spends a lot of time decoding each of these PNG files. Now, an illustration of that is to show that a single image, if you were to look at in the training data set, each of these is a PNG image file. Right? One of the reasons why this is so slow is even though in modern systems we have multiples of cores that are available, our current way of running does not use the multiprocessing capabilities. And so it's kind of one of the ways we could accelerate it is if we use the number of workers to be greater than 1 as a parameter to the data loaders, so that what can happen is multitude of these images. Each image can be conceptually sent to one core. If you have 4 cores, you could be processing 4 images. Currently, you are processing a single image, even though you have 4 cores, for example, in your setup, 4 CPU cores in your setup. So that's one of the ways you can accelerate it. But he says there are some issues with just doing that, because as soon as we do that, we get a CUDA error. And the issue is with our collate function moving on stuff. We remember use the to device on top of our collate function. And we did that. Right here. We collated it and then moved it on to the GPU. And he says that that becomes a problem because apparently there are problems of data loaders putting thing onto the GPU, but using separate processes running on different cores. And that doesn't seem to work. And that's one reason. The second reason, or the second issue that we face, is you can see, whereas in the MNIST dataset with the validation metric of accuracy executed on the validation dataset was somewhere in the 97th percentile, you can see that our accuracy for the fashion MNIST dataset is just in the mid-80s, 85.16. So that's another issue that we need to address. Both of these issues will be addressed over the next 1.5 to 2 lectures, and he will show us methods and techniques to take the results that we currently have to go from, again, we are just doing the classification problem, and the accuracy we are getting, notice it is 0.8516, which means 85.16% accuracy. He'll show us with basic engineering of just exploring each of the different techniques that one should become familiar with as we move to the rest of the course, how we are able to get this number all the way up to the low 90s and almost competitive with state-of-the-art results that are published in the public website. So that will be our journey over the next several lectures. But he currently takes a detour, and it's kind of somewhat orthogonal at this stage as to why he introduces the autoencoder at this point in time. As I said, there's much more to learn about autoencoders that we will get into. Here, the autoencoder concept is introduced just in order to motivate the changes in the framework that he begins to make in order for us to be able to experiment with networks and get quick results. So that's essentially what he uses the autoencoder that he codes in the rest of this notebook for. Okay, that said, let's look at what an autoencoder is. And for that, we switch to this image. If folks see my screen of encoding, decoding in an autoencoder.
Yeah, we can.
Okay, so an autoencoder essentially is a network, a neural network, which takes the input, and the portion of the title which refers to auto essentially says the purpose of the network is to generate an output which is identical to the input that's provided. So simply speaking, an autoencoder tries to duplicate best it can the input that's provided to it. Okay? So how do we go about providing a 28 by 28 input to of fashion and mixed images to a network and get back a 28 by 28 output which resembles the input provided to it? So we know, or so far we have seen, that by taking a series of strike 2 networks, we can reduce the output and bring it down to a 1-by-1 image, for example. Right? We have already seen that in our CNN, our simple CNN. So what we do is we take a 2-by-2 image. It could be of tree, or it could be, like a T-shirt or whatever. Using a strike 2, we reduce it to 14 by 14. Again, a strike 2 goes to a 7 by 7. Again, a strike 2 goes to a 4 by 4. Again, a strike 2 goes to 2 by 2. Again, a strike a strike 2 gets us to 1 by 1. Right? Now, that's all fine in what we do to shrink the image. But then how do we go up from the shrunk image of any given size? We can obviously intercept this process at any point. And how do we get back to a 28 by 28 image? So by 2 simple steps, he's just going to, now there are many more complicated methods that we can learn in subsequent lectures of how best to do it. But currently keeping things very simple, how do we increase the size back? And essentially he does 2 things to get back to the size of the input 28 by 28. The first step is, let's say we have a 3 by 3 output. Okay. So the size of our activation output map is 3 by 3. From that, let's assume we want to get to a 6 by 6 output. One of the ways that can be done is, remember that this is 3 by 3, so there are a total of 9 values here. This output we want to get to is a 6 by 6, so there are 36 outputs here. So one simple way to go from this 9 3 by 3 structure to a 6 by 6 36 total count structure versus a 3 by 3 and a 9 total count structure is we duplicate each of these pixels 4 times along the X and along the height and the width dimension. So what we do is we take the leftmost pixel, sprinkle it the exact same value across all these 4 values of the output, take the next image, the next pixel, it may be a white pixel as shown here, sprinkle it across this next 4, let's say the pixel next to it is black, then we sprinkle the same value across these 4, come down, take this middle left and sprinkle it across the next 4, and so on and so forth. You get the idea. But it's not good enough for the reasons we'll again get to in detail later to just do this. There's also, as he explains in the lecture, and you can go look up the terminology and the formula and what happens. There's also, just like there is a convolutional or convolution, there's also transpose convolution or a stride half convolution. But in this case, he just does upsampling, which means you take a pixel and sprinkle it across a 2 by 2 upsampling. It's called 2 by 2 because you take this pixel and put it across 2 pixels in the X and 2 pixels in the Y dimension. And then you do a stride 1 convolution across this image in order to kind of smear, if you will, and make the transition smooth. Okay, so that's essentially what you will see in code in this deconvolve layer. We saw convolve, which is essentially 2D convolution followed by activation. Now we see a deconvolve. And what does a deconvolve do? Again, the number of layers input to it is Ni, output is enough, Ns, Ks is 3, and an optional activation. The layers that we provide are essentially the upsampling in a 2D dimension with a scale factor of 2, what I just explained to you with a 3 by 3 going to a 6 by 6 as an example. And then we do this convolutional 2D of an Ni and a Nf with a stride of 1, kernel size, and a padding of Ks by 2. And if there is an activation, we conduct the activation, and then we return the sequence of these layers, which is an upsampling followed by a con 2D followed by an activation optional. That's essentially what a deconvolve does. Okay. The next thing he does, and it's not directly related to the model now, it's just a simplification of our fit function. Remember, we saw the fit function, and the fit function had the training loop in the beginning, and then the evaluation loop which followed. So we first trained the network, did the back propagation, and so on. And then once that was completed and we executed it, we kind of did the eval portion, but it was all in a single block of code. Now he just separates the eval portion, which is to be run on the valid data loader separately. So this code, if you were to go back and check the single non-modular fit function, is just the second part sliced out. So we define eval, pass it the model, pass it the loss function with validation data loader, define epoch, and then do exactly the same thing, but obviously in this case we do it with no grad because we're not computing the gradient, we're just calculating it, we're just doing inference in the validation loop. So fit function, but with a separate eval function. So the fit function becomes simpler since we have condensed the evaluation portion of the code into a single eval function call. So essentially the first part of it remains the same for epoch, put it in the train mode, take the batch values, calculate the loss, propagate the loss back, have this step of the optimizer, zero the gradient, and evaluate. The one difference for an autoencoder is what we compare the output to. Remember, typically we have labels. So for example, in MNIST, in a classification problem, we would have chosen the labels that correspond. So if you have 16 images, we would want 16 labels to be provided, so YD. But when we are trying to generate the inputs as the outputs, then our equivalent to the labels is essentially the input. So what we use to train the autoencoder is use inputs as labels. So that's the reason you see this is the outputs that generated from the autoencoder compared to the inputs. Because remember, what we want is the output of the autoencoder to be identical to the input, and the loss function to be the difference, or not the difference, but the loss function calculated as a function of the input to the push to the model. And because the desired output is the input itself, we supply that as the labels. Right? And we use, I believe, an MSE function. Now, one change in the autoencoder he makes is, given that he wants to go through a series of steps going from 28 by 28 to 14 by 14. From 14 by 14, you can go to 7 by 7. But going past 7 by 7, it's not, 7 is not an integer value, so you can't shrink it to an integer value after that. Now, in order to accommodate further steps along the way, you just pad the initial 28 by 28 image to be a 32 by 32 image. Once you do that, you kind of proceed from, you can go through multiple steps going from 32 by 32 to 16 by 16, which is a 1-2 convol. 16 by 16 takes you to a 2-4 convol. I'll comment about why he has these two layers commented out. Then a 4x4 convol from that's again a stride to, and then once you get to a 4x4 convol, you can begin to go back up again using the upsampling and the stride 1, if you will. And so you go from a 4x4 back up to an 8x8 and back up to a 16 by 16. And then you do a deconvol to a 32 by 32. And interestingly, I didn't know this. He says there's also a 0 pad 2D and a -2 passed in, which means it strips out the last two pads on all sides, resulting in a 28 by 28 image. And we take apply a sigmoid function to this output, causing everything to go, everything in our output to go between the values of 0 and 1, which is what we start off with as inputs. And we move this entire network to the device. A comment on why he has commented this out. As we run through the several cells below, he points out that for the reasons we have kind of touched on, right? The accuracy is poor, trying to do PyTorch, executing multiprocessing while also collating, those things are hard to do. And most of what we need to do in order to execute this autoencoder at speed requires that we begin to build an ability to modify the fit function. And that's the motivation for what he spends the next lecture and a half to 2 lectures setting up the framework, which is essentially called the learner, but I would call it kind of the mini AI framework or the heart of it, which allows for rapid experimentation and usage of a very flexible framework for playing with the variety of neural networks that we need to experiment with to get all the way to stable decisions. So if we were to evaluate the autoencoder, sorry, I also wanted to explain why these two are commented out. He just says that he tried to train a neural network with this, what is it? Let's see, 1, 2, 3 steps of convolution followed by 3 steps up, but he found that that didn't work. He kind of tried to reduce one of the steps to see whether he could improve the speed. Regardless of what he did, he was not able to get a good accuracy nor good speed in execution. Okay. And he shows the challenge of the results that we get, because remember, the objective of the autoencoder is to produce outputs which resemble the input. That's the goal of an autoencoder. And you can see how slowly the fit function executes. In the interest of time, I'm going to kind of continue to run these, and you could see it, but I'll talk to it. Looking at these images, you can see that the autoencoder has attempted to reproduce the input images, but you can see that it has done a fairly poor job. You can kind of see the sneaker, the tops, the ankle boot, but these are obviously not anywhere near the quality that you see of the original inputs. So besides the slowness, there's also the issue of quality, which in a sense we also saw by just the application of the convolutional part of the network, where the classification accuracy was somewhere in the mid-80s. So as I keep repeating, I anticipated much more discussion of the autoencoder network and variational autoencoders. In fact, we do that, but much later in the course. Currently, he's just using the setup as a motivation for building the learner framework. So plot that, and you can see how poor this is. versus the output. Okay, so that is the autoencoder portion of the autoencoder part of the network. Any, or this notebook, any questions again before we move to spending a little more time on setting up Runner?
Yeah, I think I have a basic question. So how would you define an autoencoder? Is it a neural network with an encoder and decoder? Just, it's been a while.
You could, yes, you could define it that way. Encoder and a decoder. The encoder portion is what holds or compresses the image, right? So it's our forward path until we get to this portion of our network, until we get to that. That's the encoder part. So we start with the network, start with the input, add it, go through 1 convolution, 2 convolution, ignore the comment, 3 convolution. So until this part is, you can think of it as the encoder. What it does is it encodes the input, compresses it, and you can do the math, right? Here, you can do the math of figuring out the size of this. It's a 4 by 4 image versus a 32 by 32 image, right? So you can do the ratio to figure out how much it's compressed the data by. And then you can think of this part as the decoder, which takes the compressed image and puts it through another neural network, which tries to generate output identical to input. So conceptually, although it's extremely simplistic, this is the encoder and this is the decoder.
Okay, and so is the fit and optimizer part, would you say, of the autoencoder, or is it like separate?
Oh, the fit and the optimizer you're asking?
Yes.
Okay.
Like,
so
is it, yeah, or is that something that's more general and just
good question.
with every model?
So correct. This is just the model, right? This is just the neural network. When I say this, I mean, for example, the autoencoder, or for example, a classifier, which was, let's go back and look at it. Did we have a classifier here? Yes. The CNN is the model, right?
Okay.
And to completely answer your question, the optimizer is just a function or a tool which we use during our training process in order to train, or, not a technical term, but jiggle our parameters using the loss function in just the appropriate right way through the propagation of the backward values as we saw in backpropagation in order to reduce the loss, right? That process that we go through using the optimizer is called training and then evaluation. There are 2 parts of it. The training part, which just propagates it takes the input, calculates the values of what the output would be, takes the loss function and calculates or applies the loss function to the calculated value of, in this case, the CNN, in another case, it could be a linear network, whatever our model outputs. That's why it's typically model XD. Compares it to the labels. In the case of autoencoder, the labels are equivalent to input XD, right? Because we are trying to generate, in that case, the output equal to input. In another case, it could be the number of labels that we're classifying. So we use those two as the input to the loss function. And our fit function is just a framework that we are setting up, or a function where we train the network in the first part and then use the train model, apply it to data that we have set aside, which is the validation data, and check how good our model performs. So the pieces to answer your question, there's a model, there's data. From the data, we get data set. From the data set, we convert it to data loaders. From the data loader, we get batches. The batches are sent, the batches and the model are provided as inputs, the data loader and the model, and an optimization function and a loss function, because we can use different optimizers. There can be an STD optimizer, and as we see, there are varieties of optimizers that we can provide to our fit function. And the fit function just trains our network and validates our network using different data. And it does this on batches of our input, and each batch consists of inputs and outputs. Doesn't it kind of explain the overall pieces as to where they fit conceptually?
Yes, thank you. This was very helpful. So basically, an autoencoder is a model, a classifier is a model, and then you use with data and optimizers to fit or measure the accuracy or loss.
Yes.
Okay, got it. Yeah, much more clearer. Thank you.
Okay, good. Any other questions? Okay, if not, let's keep moving. We still have a few minutes. We gotta get some CPUs. To be getting them easier now. Okay, so as I mentioned, the autoencoder is just a motivating function right now for us to get familiar with what we're going to do to set up a framework that allows us to experiment with a bunch of networks and get them to train quickly and produce outputs quickly. Because ultimately our goal is to be able to modify the network, modify our inputs and data loaders and data sets, and play with them in order to get to our goal of what improves the performance or what reduces the performance of our networks in order to get the networks or the models to perform better with respect to the goals we have. So keep that in mind as we go through the remaining portion. And I won't be covering the entire learner because the next lecture is devoted to learner and kind of going through it in great detail. But hopefully we'll get to the part that helps us conceptualize what we are going to begin to do to the fit function and how we modify it, how we make it flexible for experiments. Okay, so we just import a bunch of functions as before. And again, we are using the fashion MNIST data set, right? And we have a transforms, which we have seen before. We use the in-place decorator. The one prerequisite to this learner, I would encourage people to go back and look at, I think, the foundations lecture where we went through callbacks. If you weren't here when we went through that, I would encourage you to go back and listen to the recording where the callbacks, we went through them in detail and understood that callbacks could be used not just to record events as we went through various parts, but also to modify the functionality of what various portions of the code are doing as we execute those pieces of code. And we use decorators in order to accomplish that function, because decorators are functions which return functions, or classes or callables which return callables. And by that, what we try to do is we send in a callable. A callable is a function or a class which can be called, which means that there is, the parenthesis following it. And when we pass a callable to a decorator, what we get back is a modified callable. Okay, that's something that I think you need to get very familiar with, as callbacks are used extensively in the learner framework. Or all we do here is set up a batch size, and as we've seen before, do the transformation, and then we do the data loaders from DD, convert the converted data set, or the transformed data set, I should say, provide the batch size, and we don't, as I mentioned before, we could kind of accelerate this somewhat by using multitude of number of workers. Therefore, we provide the number of workers to be 4, and then we take the training portion of the data loaders, we extract a batch, and then we look at the shape of the batch. Right? Because the batch size is 1024 and our images are 28 by 28, you would expect the input to be 1024 by 784. And the YB are just the first n labels, because we don't want to print 1024 labels, the indices to the labels, if you will, and these are the first 10. Right? Now, oops. For the get PLS code. My apologies. Issue, but it have been defined. Let's try them. If it doesn't work, we start with this at our next. So figure this out offline. I don't want to. Basically, the mini AI installation should get me the get PLS function. Not being that is Okay, so I am just going to give you a quick explanation of this learner, but I'll once that's finished, since I'm unable to actually run the code and show you, what I'll do is make sure to analyze what the issue is with this notebook and why it's not able to recognize the test function, whether something got changed in the notebook. But let me just quickly explain what the learner function does and how he has coded it, and walk you through the sequence of things that happen. And then we'll start by actually being able to execute the code rather than running into this why I'll debug offline rather than wasting all of it. But let's kind of basically go through the learner code and understand the sequence of steps it follows and how he has coded it. The learner replaces a fit function, okay? And the learner is passed a model, and to the earlier question, there are these pieces that are passed to a learner: a model, data loaders, a loss function, a learning rate, and an optimization function, or an optimizer, okay? Which could be, in our case, the default is STD, but it could be any one of other optimizers as well. And this basic learner is rather inflexible, but we'll understand as we move through how to build a much more flexible learner. But let's see how the code in the learner executes. So we pass these, and using obviously the fast post store attribute rather than write self.model, model, self.dll, DLS, this single line of code stores all of these values in our learner. So now the first thing is we start with, let's say, learner.fit, and we pass it the number of epochs, right? Then, at least currently, our learner is just set up to do two things: calculate the loss, and it's kind of useful only for classification problems. So it just calculates our accuracy. So it kind of creates the list to store the accuracy values, the losses, and the number of items that we pass through in each batch. We move the model to whatever device we choose, that is, we move it to the GPU. We pass or create an optimizer using the optimization function, which if we pass to it, in our case, the default is STD. And remember that the optimization function requires the model parameters. Since we have passed it the model, it can obviously extract its parameters, and we pass it the learning rate. Learning rate is also passed in to the learner. Then we store the number of epochs, and for each epoch in the range of the number of epochs, we first say self.oneEpoch and pass it the value of true. So we move to what does one epoch do. So this is what the fit function, then the one epoch function. The one epoch has the parameter train. Since we pass it through, that means it's in the training mode. So it says, hey, take the value of train, stick it in the model's training flag. So train is true, self.model training is true, which means the model is in the training mode. Make sure the data loader is a train data loader if the train flag is set. Otherwise, it's a validation data loader. And then for each index and batch, when you enumerate, you get two values, the index and the batch, in the data loader. So obviously, remember that if training is true, this will be a training data loader. If the batch from a training data loader, if not, it will be a batch from the validation data loader. So it can execute self.oneBatch. So remember, from fit, we came to one epoch. Now, when we go here, we load the data loader, but then we say call self.oneBatch. So from here, we go to one batch. So what does one batch do? Well, it moves our batch to the device, which means it moves the data to the GPU. Then, since the model is already known to the GPU, it executes the model on the inputs, both are in the GPU, collects the predictions, using the predictions and the labels, which it also is recovered from the batch. It computes the loss and the remaining executes the remaining steps of training, right? If it's in training mode, propagate it backwards, step the optimizer, zero the gradient. And if it's not in training mode, because it could be in training or validation mode when it comes here, if it's in validation mode, do none of this, but just with .NOGRAD, calculate stats. That means now using the validation data set or data loaders, we just want to calculate the stats. What does calculate stats do? It calculates the accuracy using self.predicts argmax dimension equal to 1 is labeled. So again, try to go back and understand why this works and why the sum of these function gives you the accuracy. And then it just appends the accuracy to the list of accuracies, which was an empty list we created, calculates the length of each of the batch and puts it in N, calculates the losses and multiplies the loss by the number of values in the batch and sticks it in the loss list, and then appends to the total running count, the N, right? That's what the learner function as it is currently set up does. I would encourage you, each of you, to again chase through the code and understand what sequence of steps this simple learner or inflexible learner goes through before we start our next lecture. I think that should help you to get an idea of what, when we use the learner, what we do with it. Because then we could just create the model with M and NH, create a sequential model, which is the linear model we had, pass the model, the data loaders, the loss function, which is cross entropy, a learning rate to the learner, create an instance of the learner, and remember what when we call learn.fit, we pass it the number of epochs, which is 1, and then it goes through the sequence that I just described, which is fit, calls this, that calls 1 epoch, it executes the 1 epoch code, which calls 1 batch, which executes this, which could be in training or in eval. Obviously, it first goes through training. Training doesn't call the cal stats, returns, does the NOGRAD self.1 epoch again, goes through the 1 epoch code, which calls the 1 batch, but this time in validation, which helps us calculate the statistics, and out pops the 0. The true is because it is training, and the values, which is the loss and the accuracy, 0 false, then the loss and the accuracy. Right. So the important thing is it's a very inflexible setup, but the setup is something that we modify and build incredible amount of flexibility around this learner concept. That's what we'll begin to do in the next lecture. Apologize for this sudden issue that I ran up into, kind of strange because I've executed this notebook multiple times, never run into this problem. So I don't know whether something in the underlying books or something has changed. Paste that down offline. Any questions before we log out? No, thanks for joining. We'll start with the learner, the metrics class, and a whole bunch of details of how we modify the learner in our next lecture next week. Thanks for joining, everybody. Have a good weekend.
Thanks.
Thank you.
Bye. Take care.